reviewing is the one on forecasting turbulence. The mystery of fluid turbulence has eluded scientists to this day. Great minds like Da Vinci and Heisenberg could only make attempts at unraveling its secrets. Dr. Michael Schatz lectures about the modern-day search for the answers to fluid turbulence. Dr. Schatz mentions a formula known as the Navier-Stokes equation. This equation, a derivative of Newton's second law of fluids, is a formula to describe fluid flow. We've had this equation for over 200 years at this point. That makes it even more interesting that we still don't quite understand turbulence. Dr. Schatz goes on to explain that the Navier-Stokes equation unfortunately does not follow the rules of superposition. Superposition in this case is adding simple solutions together to create one complex solution. This can't be done with Navier-Stokes because the terms are non-linear. The example the doctor used was one of two guitar players playing slightly out of tune, which piqued my curiosity. I know that in chorus, a singer will match a note by listening for the sound of the oscillation caused by the superposition of their sound waves with the sound waves of which they're trying to match. This principle makes sense with something like sound waves, but can't be applied the same way to fluid turbulence. Dr. Schatz uses Lorentz systems as examples as well. These systems model chaos, and the entire system can be understood by understanding the variability of the system, or each possibility presented. Lorentz systems have only 3 degrees of freedom, whereas something like turbulence has multiple magnitudes more. Turbulence is more on the scale of thousands to millions of degrees of freedom. While this scale makes it seem like it would be impossible to solve the mystery, patterns have already been discovered in this chaos. One discovery was made by mathematician Andrei Kolmogorov using magnetic array in opposite directions that were placed in an alternating pattern. I know that when there is a current with a magnetic field around it, a Lorentz force is produced. In this case, the force moving upward on the plane moves back and forth due to opposite-facing alternating forces. This scenario created a situation akin to 2D turbulence, which Kolmogorov was able to study. Modeling can be done completely differently due to more advanced technologies being created. We can now use high-speed cameras to model turbulence. This way, that scientists have been slowly moving towards finding solutions has been brought with it the realization that this might not be a roadmap to an answer. This will more likely be a mystery that uncovers future mysteries. Dr. Schatz shares some cool visuals near the beginning, using water droplets as examples. The body of water is oscillated while a single droplet interacts with it. The droplet doesn't interact in the way you would normally think, but I recommend you watch it to see what happens. I knew that turbulence was one of the big unsolved problems of physics, but I never knew why or the background surrounding the research. It was interesting to hear about how turbulence related to other issues, like how to move an object. He mentions that the energy needed to move something, like a car, is mostly a result of drag from turbulence flow. This means that with greater understanding of flow and how to reduce drag as a result, we can use less energy on machines like vehicles. This actually relates to my major of industrial engineering, where our main objective is to increase efficiency. Being able to leverage knowledge on turbulence to decrease something like fuel required is surely a way to create more efficient vehicles. I honestly watch a lot of physics YouTube videos in my free time, and this lecture definitely makes me want to find some turbulent flow. I really recommend everyone check out this lecture.